All right, here are some examples that we're going to do for radioactive decay. These are relatively simple examples. That's why I chose them. All right, so the first one we have plutonium 240, which is undergoing an alpha decay. And so what we want to do is we want to balance um, the reaction. This is of course a nuclear reaction. It's not a chemical reaction. So we were balancing a nuclear reaction. Let's just make sure that we're clear about that. So let's take a look at this first reaction. We have plutonium 240. That's of course this top one right here. So the 240 is the number of nucleons. Plutonium, if you didn't already know, is element. Let's assume that we didn't know that actually. Here, I'll show you. Remember. Let's see. So if you look on the periodic table, how did I get the periodic table? It's really simple. Go to Google, type in periodic table of the elements, and this comes up. This is actually part of Google now. And so here is plutonium, right? So plutonium is element 94, all right? So let's keep that in mind when we do this. All right, so plutonium is element, so let's see, so here's what we're gonna do. So plutonium, which capital P, lowercase u, 240, and of course it's element 94. So that decays into an alpha particle. So an alpha particle, of course, is just a helium nucleus. So helium has, of course, 2 protons, and it has 4 nucleons, which is the number of protons plus the number of neutrons. All right, so this is going to be plus. All right, so we're going to have some element where this, it's really simple. Like you just take the subscripts, right, on this side of the arrow, which is 94, has to add up to the subscripts on this side of the arrow, right? The same thing with the superscripts, right? The 240 has to add up to 4 plus some number, and so that's really easy. And so this one of course would be element 92. All right, so now we're going to look that up. So element 92. I mean, I happen to know that that's uranium, but let's just check that just to be sure. So if we go to the periodic table, see 2 down from plutonium is of course uranium, which is element 92. All right. So this is going to, of course, this is going to be. We just figured this out that this is uranium, which is just a U, and the isotope of uranium is of course it's going to be 240 minus 4, so of course it's 236, right? So 236. So this with an alpha decay of plutonium becomes an alpha particle plus uranium 236. All right, so let's do the next one, which is xenon 131. All right, so xenon, which is a noble gas, just to let you know, 133. Sorry, xenon 133, and we got to look up xenon, which I don't know off the top of my head. So it's in this last column. These are all the noble gases. So xenon is element 54. All right, so that's the subscript. So it's 54. See the reason that you don't have to put the 54 is because the 54 and the capital XE mean the exact same thing, right? Element 54 is xenon, right? And so it's undergoing a beta decay, right? So that's just an electron that comes out of the nucleus. So its charge is -1, and its nucleon number, because it's an electron, it doesn't have a nucleon number. So we already know that whatever element this is going to become, is its nucleon number is going to be 133. Why is that? Because we got 133 right there. And, 0 plus 133 is 133, right? And then, of course, this one, this is going to be one less, sorry, it's one more, right? So, the element here is one more. So 55 minus 1 is going to give us 54. So this is going to, whatever element is 55, and we'll look that up in just a second. That's the symbol that goes here. All right. So this is all part of this. This is all part of what you do. So remember, there's xenon. So the next element right here is going to be cesium. All right. So there's cesium. So you put a capital C, lowercase s. All right. So that's going to go. So that's cesium. Cesium, that's supposed to be an S. Sorry, it doesn't really look like an S. Cesium 131. I'm sorry, so cesium 133. Cesium 133. All right, so let's do the next one. So we have PO, which is polonium. All right, so if you don't know that, that's fine. So it's polonium 214. 214. All right, so let's see what the chemical symbol for polonium is. All right, so here we go. So polonium is, there it is right there, right next to bismuth. So polonium has 84, right? It's right there, 84 protons. All right, so we can go back here so that we put an 84 down here. 84. And it says, this problem right here says it undergoes an alpha decay. So it's very similar to this one. So if we undergo an alpha decay, and so this becomes, a helium. This breaks apart into a helium nucleus. So there's the helium. That's the alpha plus. All right. So again, we just you just add up. So this is just going to be the number that's going to go in the subscript is 84 minus 2, or 80, of course, 82. Right? So 82, which I'm pretty sure that's lead. And then this one will, the number of nucleons will be 210. 210. All right. So again, since it's 82, we got to look that up real quick just to make sure. See, and there it is. 82 is the symbol Pb, which of course is lead. All right. So we put the Pb right there, and so this is lead. Pb. Sorry, Pb. So that's lead. The way you would say that is it decays into an alpha particle and lead-210. All right, let's see. So we still have one more to go. So we have bismuth, 214. And if I remember correctly, bismuth, well, I don't have to remember, right? We can just look it up. I think it's 83. But so here's bismuth. It's right there. So it is element 83. So that's the subscript that goes right here. So it's 83. Bismuth 83. And it says it's undergoing a beta decay. So it becomes an electron, no nucleons, and a -1 charge. So for it to get a -1 charge, that has to be the next element up. So it's going to be plus, so it's going to be 84, right? 84, and then 0 plus 214. So that's going to be 214. 214. All right. And what, that's supposed to be a 4. 214. All right. And so what is element 84? So let's look that up. Element 84 is, where is it? Polonium, right? There it is, polonium, PO, right? So that's the symbol that goes right there, polonium. All right, so you put a PO, remember it's capital P, and it's supposed to be a lowercase o. All right, so a beta decay of bismuth 214 becomes polonium 214. All right, so that gives you some examples. All right, so here's our next example. Suppose we have nickel 67, and it has a half-life of 21 seconds. If a meteor crashed into Earth containing nickel 67, and it started with 4.3 times 10 to the fifth grams of this radioactive nickel, how much nickel would remain after? Oops, I forgot to put. Sorry, I had to paste. Okay, so it's after 3.15 minutes. All right, so it didn't paste very well, but we can go with this. All right, so anyhow, t is the amount of time that has passed. That's the 3.15 minutes. Now we're going to remember t and t1/2 have to be in the same units. So it'll be easier to convert 3.15 minutes to seconds. And then, of course, the half-life is 21 seconds. And the starting amount, that's what n sub 0 is this many grams. So the remaining amount will be in grams as well, right? Because we're not changing that. All right, so let's write what we know. All right, so I've written some of what we know. The initial amount in this comet of nickel 67 is 4.3 times 10 to the fifth grams. I just wanted to write this in a slightly different way. This is more the way you enter it in your calculator. 4.3 E, usually capital E, 5, which just means times 10 to the fifth grams. And the only thing that we have to do is we have to convert minutes to seconds, but that's really easy. The conversion, everybody knows that there are 60 seconds in 1 minute. So the minutes cancel. All right, so this 1 minute cancels there, and so 3.15 times 60. So I just did it in this little calculator right here. So 3.15 times 60 is 189 seconds. All right, so let's write that down. So it's 189 seconds. All right, so now, and the half-life is, of course, 21 seconds. All right, so here, I'm gonna get a little bit of room here so that we can complete this problem. But you just keep in mind, you got this is really the only calculation we've done so far, is that the amount of time that has gone by is 189 seconds. All right, so we're going to find that that's important. All right, so let's just write this out. So we were looking for n, right? N is the thing that n is what we're looking for. And so the initial amount was, so it's 4.3 times 10 to the fifth. So 4.3, I'm going to write it this way, 10 to the fifth. Just get used to that, right? This is grams, and then it's 1/2 raised to the power. All right, so let's see what it's going to be raised to. So remember, we figured out the amount of time that has gone by. Let's get to the calculator here. Was 189 seconds. So 189 divided by the half-life, which happens to be 21 seconds, right? It says it right there. There's the half-life, 21 seconds. All right, so now we're going to see something very nice. So remember, this is a general formula. In this particular instance, the 21 goes exactly into 189 seconds. It goes in 9 times. So 9 half-lives it has undergone 9 half-lives. The lab that we do using the coins, that would be like flipping the coin. The chips. It'd be like flipping the chips 9 times. All right. Anyhow, this is the amount. So let's figure out what this is. Okay, and so you raise 0.5 to the 9th power, and you multiply by 4.3 times 10 to the 5th. that you get